I'd like to talk to you about metallic bonding. Now, metallic bonds form when metal atomic cores, along with their valence electrons, join metal atoms and form a sea of electrons. Now, let me explain what all that means. The atomic core is made up of the nucleus and the inner core electrons, valence electrons being the outermost electrons. And it's those outermost electrons that are able to form what has been called a sea of electrons. Now, there's a term for that. These are delocalized electrons. As you can see in this animation, electrons are able to move throughout the metal sample. That's what is meant by delocalized electrons. And they form when there's overlaps in orbitals. So if we look at this schematic here, let's call this sodium. So to help you understand, I'm going to do an electron configuration for sodium. Now, sodium has one valence electron. You know from your studies of electron configurations and quantum numbers that two electrons can fit within the s subshell. Sodium only has one. Those orbitals all overlap and lead to these delocalized electrons. Now, the metal is held together from the attraction of the delocalized electrons to the positive charge of the nucleus. So you can imagine that these electrons are able to move freely throughout the sample, forming again what has been called a sea of electrons. Now, let me talk to you about some properties of metals, and you're going to see I'm going to keep coming back to these delocalized electrons and sea of electron model for metallic bonds. So metals have a high conductivity, and that is because their electrons are delocalized. So electrons are free to move around, and electricity is flowing electrons, flowing charge. So it shouldn't be a surprise that metals are great conductors of electricity. Metals are also very strong, and they have high melting points. Now, to make sense of that, I want to look at the sea of electrons for two samples. One is a group 1 metal, one is a group 2 metal. And to use the same example, let's call the group 1 metal sodium, the group 2 metal magnesium. They are in the same period on the periodic table. Let's start with the group 1 on the left. So what do you notice when you compare group 1 to group 2? Well, you should notice right away group 2 has twice the electrons. And that should make sense because group 2 metals have 2 electrons in their outer subshell. So they have 2 valence electrons. And it's the valence electrons that make up the delocalized electrons that form the sea of electrons in metallic bonds. So now look at the nuclear charge. Okay, so group 1, we'll call it plus, but group 2 have one additional proton in their nuclei. That means they have a greater atomic charge. And what makes metals strong is that attraction between the delocalized electrons and the positive charge of the nuclei. So it shouldn't be any surprise for me to tell you that magnesium has a much greater melting point than sodium. Other properties would include malleability. Again, this can be explained by delocalized electrons. So if I were to take a hammer and pound a metal, I could change its shape without breaking it. The reason being is that the nuclei are changing shapes and the sea of electrons are simply conforming around them, maintaining the identity of the metal without causing it to break. Ductility is very similar, and it's referring to the ability of a metal to be stretched into a wire. So, the last one I want to talk to you about is luster. So, metals are opaque and they're also very shiny, and this can be explained by the sea of electrons. The outermost electrons, those valence electrons, will actually reflect light with the same frequency that hits the metal, giving metals their luster or shine. So in this video now, we've continued our discussion of bonding. We've talked about collision theory. We've talked about ionic bonds, covalent bonds, polar covalent bonds, and now metallic bonds. I wonder what could be next. I'll see you guys in class.